So the talk is in two parts. The first part is a bit of an introduction to model selection and some results on model selection methods, and then the second part of the talk is looking at some recent results for model selection problems on large-scale problems. And that's the second part is joint work with Alec Agarwal, John Ducci, and Clement Levrun. All right, so just to give a motivating problem, a prediction problem, let's think about the problem of deciding what ad to serve up on a web page. So we have features of the web page, features of the candidate advertisements, and we want to decide what's an appropriate advertisement to serve. We want to predict something like the probability that a viewer will click on an advertisement. We have this clickstream data available that tells us what advertisement web page combinations were clicked on and were not clicked on, and we want to use that to make our decisions, to build a model to somehow make those predictions. So for instance, we might train up a big logistic regression and use that for our estimate of the probability. So let me start by telling you how we can formalize prediction problems of that sort and where the model selection issue comes up. And then I want to talk about results in model selection, things called ora-cle inequalities, settings where we can get fast rates for these ora-cle inequalities. In the second part of the talk, I'd like to tell you about some recent results for large-scale problems. So that click prediction is an example there where the amount of data is huge, where the perspective of many of these classical results, I think, is the wrong one. So in a lot of the results for model selection, we're talking about how to solve the problem optimally as a function of the amount of data, and the argument I want to make is that that's the wrong perspective, that when we're in a setting like that where we have for instance, clickstream data, we have a huge amount of data, essentially unlimited, and we should be thinking about performing optimally with respect to the amount of computation that we can afford to spend. So that's the big message of the talk. So let me start by saying a little bit about prediction problems and how we formalize prediction problems in a probabilistic setting. So we have data. We're assuming that it comes along as a independent, identically distributed sequence. So from some space, I'm just calling these the data Z1 through Zn. So for instance, these might be XY pairs. The X might be features of the advertisement and web page, and the Y might be an indicator variable that tells us whether somebody clicked or didn't click. The idea is to use, let's say, n of those data points, Z1 through Zn, to choose some action that we would take. I'll call it f sub n because typically we're thinking about predictions, functions that map from x's to some space of different decisions we can make. We're choosing f sub n, and we'd like it to have small risk. And what do we mean by that? Well, we want the cost of those decisions to be as small as possible. So here we're going to measure the cost by thinking about, by defining a loss function L, right? And that's defined on the space of actions that we can take up here and the space of the data that we can see. We get L for Fn comma Z is the cost of making that decision when this is the outcome that we see, and we want the expected cost, we'll call that the risk, to be small. So we'll use this notation, capital L, to be the expectation of little l. All right, so for instance, we might be thinking about estimating probabilities of clicks and measuring our performance by saying, well, if we have some mapping F that takes us from the space of features of advertisements and web pages to a real number between 0 and 1, and we'd like that real number to be a good estimate of the probability of a click in the sense of minimizing this expected squared error. Or we might want to make an actual decision And our loss function might be the indicator for making a mistake. The outcome here differs from our predicted outcome. All right, so we're deciding there on the most likely class label. Might not be such a good loss function to use in the case where people are very unlikely to click on any given advertisement. But this sort of setup is more general than just thinking about predicting in a classification problem of this sort. You can cast density estimation problems in this sort of way. For instance, we might think of F as forecasting a probability distribution, a density with respect to some measure, and we incur a cost of negative log of the predicted probability of the actual outcome. Right? And so minimizing the expectation of that is the same as minimizing the Kullback-Leibler divergence between our forecast distribution and the actual distribution. Okay, so there are some examples of problems that can be formulated in this way. And our aim is to choose this function fn with small risk. Well, we're typically choosing that, or make a decision here that has small risk. We're typically choosing that from a class. In the prediction case, we think of that as a class of functions. So for instance, in linear regression, it might be linear maps from our feature space to the reals. Logistic regression, we have our squashing function. All sorts of other things support vector machines. We might think of that as a class of functions in some a subset of some reproducing kernel Hilbert space. And in fact, although I'm talking about this class as being all linear maps from this space, or logistic regression without constraints on the parameters, or anything in the reproducing kernel Hilbert space, typically we're going to be doing some sort of regularization or restricting ourselves to maybe functions with sparse support, or small parameters, or constrained to small balls in a reproducing kernel Hilbert space, for instance. All right, so that's a sort of formulation that I want to deal with, and some examples of problems that can be posed in this way. And we're trying to find make a decision here that has small risk. Well, let's think about the best that we can achieve. The Bayes risk is the minimizer over the whole space. In the prediction case, we might think of that as all measurable mappings from the space of patterns to our decisions. We want to come up with the best, something that's as close to this best risk, this minimal risk as possible. Well, we can decompose the excess risk, the risk that we get from a particular estimator versus the best possible, into two terms. There's the best that we can do given that we're making our decision from some restricted class, capital F. Well, that's something inherent to the problem and to the probability distribution that we're facing, and inherent to this class of functions. That's the approximation error. Right? That's how much worse than optimal we are because we're restricting ourselves to this class for that particular problem. And the second term here is the estimation error. That's telling us how close we can get in risk to the best in the class. And this is the statistical quantity here, right? This is the cost of seeing the distribution only through the window of our sequence of n data points, right? And because of that, we have a non-zero estimation error. If we had complete knowledge, this is how well we could do. All right, and there's a trade-off between these two terms. If we choose a richer class F here, so in the ad prediction case, if we're including more and more features in our representation of web pages and advertisements, then we can get a smaller and smaller approximation error. We're going to get a better approximation to the optimal decisions that we could make. On the other hand, as we increase the size or the complexity of this class F, we're going to incur a statistical cost. The estimation error is going to go up because we're working with a richer class. It's a more difficult estimation problem to come up with an F hat from this finite amount of data, right? Z1 through Zn. And so the model selection question is all about choosing automatically the class F so that we get a good trade-off, right? We want to somehow choose a class that's not so simple that our approximation error is huge, but not so complex that our estimation error hurts. So that's the trade-off that's really at the heart of the model selection problem. So let me give a couple of examples before I formalize that problem. So the case of linear predictions, there are lots of, in classification problems, there are lots of linear classification algorithms that work to minimize some sort of a empirical estimate of risk subject to a constraint on certain parameters. So for instance, we might look at, I've used the same symbol L here, but maybe this is not necessarily the same thing. We might look at a sum over the n data points of the loss incurred for this outcome for a certain choice of our parameters. We might minimize that choice subject to some constraint. In this case, we're thinking about the parameterization as being linear, and we're looking at a norm being bounded. So, for instance, SVMs work in this kind of a way when you choose your linear space appropriately, support vector machines. And so those two terms, the estimation and approximation terms, depend on the bound R. This is a natural notion of complexity. When we consider constraining our parameters to a smaller ball, we get a simpler class. Our estimation error goes down. Our approximation error gets worse. Right? And often in practice we'll choose these parameters, from some set, and that's the model selection problem that arises there, is choosing an appropriate value of R. Maybe I should say, in many cases we can think of this optimization problem, a constrained minimization, alternatively as something like a Lagrangian. Minimize this empirical risk term plus a penalty term defined in terms of this quantity, right? And for some appropriate value of the weighting of the penalty term versus the empirical risk term, we have an equivalent optimization problem to this constrained one. But then of course the choice of the constraint R becomes the choice of the weighting in front of the norm term. All right, another example we might consider is feature selection. Again, thinking about a parameter space, and we want to consider some subset of those parameters. All of the examples that I'm going to be talking about are cases where there's a natural ordering on these parameters, and we're considering when to stop including extra parameters. So for instance, in natural language processing, we might think about unigram models that look at just a single word, or bigram models that look at pairs of words, or whatever. What's the value of k here when we want to go to k-grams. In function fitting, we might look at polynomials of different degrees, Fourier bases of different dimensions, and so on. And similarly in computer vision, in many other applications. And again, the approximation and estimation errors depend on this dimensionality. That's a natural notion of complexity here. As we increase the dimension, the class gets richer, and we decrease the approximation error. But the estimation error term is going to increase, where we have a more difficult estimation problem as the dimensionality goes up. All right, so that's the model selection problem. We're thinking of it as a hierarchy of these classes or models. So, for instance, in the constrained linearly parameterized problem, these classes correspond to linear functions with an increasing bound on the radius of the ball we're considering. And we have our data here, and we want to choose. I've written this as an I star, an index of one of these classes, but you can think of it more generally as just picking a function from somewhere in this hierarchy, and we want to pick that function so that its excess risk is nice and small. In particular, the right way to think of it is it gives a good trade-off between these approximation and estimation error terms. As we consider richer and richer models, we have a smaller approximation error, but we face a potentially worse estimation error, and we'd like to make that trade-off in some way that's somehow optimal. Okay, so here's one example of an approach to model selection. And this is looking at introducing a complexity penalty and minimizing an empirical risk term. So it's a natural thing to do. You know, in the linear example, linear pattern classification approach I described earlier, it was already there. We minimize some kind of empirical estimate of the risk. Right, so this is just a sample average, an average across the data of the losses that are incurred. So this is the risk under the empirical distribution. So that's a natural thing to consider as a criterion. We might think of choosing a function fni from, or making our decision fni by choosing the f from the ith class that minimizes this empirical risk. And then when we look across all of our classes, we might minimize a combination of the empirical risk plus some kind of penalty term. And we want to have a penalty term there because as we move up the hierarchy, we know the empirical risk is going to go down, but we're going to incur a bigger and bigger estimation penalty. And we want to take that into account by including some sort of a penalty for going to more and more complex classes. And there are many examples of complexity penalties here that we can use. I'm going to look at a very simple example that's based on bounds on, so uniform deviations between expectations and sample averages, but there are lots of other examples. You know, the aka information criterion, for instance. You know, these kinds of things that appear. So this gamma I of n, this penalty term, is something that we would expect to increase with the complexity of the class fi, and decrease with the sample size n. All right. So as we see more data, we're going to incur. We need less of a penalty because our empirical risk becomes a better estimate of the true risk. See, what we'd like to minimize over here is the true risk of the functions that we see from the ith class. And this becomes a better estimate as the sample size grows, and as the complexity increases, it becomes a worse estimate. So we can state things generically as this complexity penalty, but here's an example of a complexity penalty. If we have a gamma I of n that gives us an upper bound on maximal deviations between expectations and sample averages. So when we look across the class fi, the worst case deviation between the risk, the expectation of this loss function, and the empirical risk, the sample average, across these n data points, z1 through zn. We look at the worst case deviation. If that's bounded by something like gamma I of n, with high probability, the probability is with respect to the sample here, right? We're seeing a random sample of size n. If those deviations are bounded by gamma I, then we can choose a complexity penalty that's exactly gamma I. And so on each of the classes fi, we're minimizing the empirical risk, that's this function, and then we penalize the empirical risk that we see by this penalty, which is a deviation between the empirical risk and the true risk. That minimization leads us to a function f hat that has risk that's bounded by this quantity. Okay, so what's this inequality saying? Well, this is the best across all of the classes of the, this is the minimal risk in that class. Here's our complexity penalty, and then there's an extra term there. Okay, so we're getting an upper bound here that tells us how good this output of our model selection scheme is. These are called ora-cle inequalities because we can think about the inequality that we started with that tells us, look, the maximal deviation between expectations and sample averages, between empirical risk and true risk, is bounded by this kind of quantity, right? And that tells us that, well, the risk of the minimizer for that class is no more than the best in the class plus something like twice this quantity. And why is that? Well, that's straightforward. If we look at the risk of this best guy, that's certainly within this much of the empirical risk of this best guy, and that empirical risk can't be better than the empirical risk of the minimizer. And the empirical risk of that guy is close to its true risk, right? So this quantity is close to the empirical risk of the minimizer through this inequality, and this is close to the empirical risk of this guy through the same inequality. So we get kind of twice the penalty here, and the constants have changed from line to line. Okay, so this is just immediate, but that's telling us that that's true for every, for each model we have this sort of a bound, and our ora-cle inequality is saying if we use this complexity regularization, then we come up with a decision f hat that looks like the best of all of those bounds, right? These are the inequalities that we saw up there, with a small increase here marked in red. I've put that as a k. I could have put something. I could have put an I in here, which would have been a little less confusing. So k, think of k as the number of these models, right? We're picking from f1 through fk, but it's not essential that we consider a finite hierarchy. So we get a small penalty here. This is kind of logarithmic in the terms of interest. We get a small penalty here for doing this, for automatically choosing the class, and that gives us a bound on risk that's close, modulo that little penalty, that's as good as the best of these inequalities that we had on our these upper bounds we had on the risk for each one of these different classes. So it's as if an ora-cle had told us which one of the classes gave us the best trade-off between approximation and estimation error terms, right? Which I is the right one, and then we can use that one and get an inequality that's at least as good as that, or not too much worse than that. All right, so that's the flavor of result that many people have proved for many different model selection schemes, and I've given you, an outline of a proof for this particularly simple generic approach to model selection of complexity penalization. So I want to say a little about faster rates, working with faster rates than the rates that are implied by these sorts of uniform convergence bounds. So ora-cle inequalities for these kinds of schemes, or the ora-cle inequalities that I've told you about, rely on bounds on maximal deviations between risk and empirical risk. And this worst case across the class nature of these inequalities it can be a pretty clumsy approach. Typically the fluctuations that you see between these quantities are at least of the order, even for very simple classes, they're at least, I should have put an omega there, right? They're at least as big as 1 over square root of n. And you can't improve on, oh, I see, yeah. So you can't improve on this 1 over square root of n in using this sort of approach, because that's the lower bound on the order of magnitude of these kinds of deviations, the worst case deviations across the class. And in some cases, that's the best you can do. These sorts of complexity penalization approaches based on uniform convergence results are optimal, but in many cases, actually you can do better than that. You can do better than is implied by these worst case deviations. So just to explain how we can do better and where these improvements arise. So if we're working with simple classes that satisfy some certain properties, I'll say a little about that in a moment. But in many cases, we can get results of this form, right? Where for a simple class, the maximum deviation between the excess risk across all functions in the class is bounded by, this is not the the excess empirical risk, it's some constant bigger than 1 times the excess empirical risk, right? This is the difference between empirical risks for that function, and the f star is the minimizer of risk in the class. And the deviations here, right, because we have a factor bigger than 1, the deviations here can be much smaller than the 1 over square root of n that we saw in those previous results. And if you can get an inequality of this sort, it turns out it's straightforward to show that minimizing the empirical risk across the class gives a risk that's this far away from optimal. And if you think about that, it's not too hard to see why. When you minimize the empirical risk, right, then this guy's certainly going to have a bigger empirical risk, the optimal function in the class. So this quantity is non-positive. And this is just the excess risk then for the minimizer. That should be an f hat, right? The minimizer here has risk better than that guy, plus this quantity. And so getting inequalities of this sort is possible in many cases. So the particular rate here, log n over n, is for a simple class. So for instance, finite dimensional kinds of classes, where we have some sort of a relationship between variance of excess loss and expectation of excess loss. And that arises in lots of cases where things are kind of smooth and regular somehow. So for convex losses, loss functions that satisfy some uniform convexity condition, you have results of this sort. So for instance, quadratic loss, or there are many examples where you have this sort of relationship in regression kinds of problems, also in classification problems with low noise. So this kind of Mammon and Tsibakov called it a margin condition. So where the probability of the conditional probability of a certain class label being right at the boundary is small. If you satisfy that margin condition, then you can get inequalities of this sort also. So these things arise in several different settings. So here you can also exploit these kinds of inequalities in getting ora-cle inequalities for model selection schemes. So it turns out you can just use complexity regularization to exploit those faster rates, provided that the hierarchy you're considering, so the system of sets here, is ordered by inclusion. So if these models are all contained in each other, and this is essential, then this is a little ugly to look at, but if we just ignore these parts for a moment, what are we saying? The excess risk of any function in the class, this is the best in the class, the minimizer of the risk, this fi star. The excess risk is bounded by, so let's put the inequality in here, is bounded by some constant bigger than 1 times the excess empirical risk plus a little penalty term, right? So that's the kind of inequality we saw back here, right? If that's true for all of our classes, and we have something on the other side, right? So empirical risk in terms of true risk, some sort of inequality of that sort, then just minimizing the empirical risk plus a complexity penalty across all of our classes gives us something that's within this complexity penalty of the best. All right, so best inequality across all classes that would be implied by these inequalities. Right, so we get an ora-cle inequality of just the right form. Right, this is the output of our model selection scheme, and its risk has a bound that's close to the best of any of these risk bounds. So we can cope with cases like that where the rates for uniform deviations are suboptimal. Okay. So, that's just to kind of belabor the point. It's kind of interesting that this happens when we work with, it's really very different from the first kind of model selection scheme. When we're working with empirical risk, we know that this empirical risk is bouncing around on a scale of 1 over square root of n, right? This is just the order of magnitude of the deviations there because we've got this random sample of size n. And what we're doing here is adding a penalty. For the case of a small class, we're adding a penalty that's like order 1 over n, right? Adding in this tiny penalty compared to the scale of these fluctuations is giving us an estimate that has risk within, this very small amount of the best. And the reason is that when these models are ordered by inclusion, we have the fluctuations are correlated. And something to notice here that's going to be important for the later part of the talk, these empirical minimizers, the correlation occurs because the empirical minimizers across the hierarchy here are chosen using the same data, right? And so, we have this very, very strong relationship between what happens on the data for a bigger class and what happens for a smaller class, because that class those classes are ordered by inclusion. Okay, so that's what I wanted to say about the problem of model selection and some of these results for model selection. The flavor of results for model selection schemes, these ora-cle inequalities that tell us we can predict, we can come up with a choice that's almost as good as that gives us a risk bound that's almost as good as the best bound that we could have got if an oracle had told us which model in the hierarchy we should be working with. So I want to switch to the second part of the talk, which is all about model selection problems in a large-scale setting, so where we have an abundance of data, and looking at model selection schemes from this perspective where instead of working optimally with respect to the amount of data that we have, we want to work optimally with respect to the amount of computation that we have. So by way of motivation, and that's probably, in this setting, it's probably redundant to tell you about the large-scale problem, but let me zip through it anyway. So there are lots of cases, and the click prediction example I started with is one. There are many cases where we have an amount of data that we can view as effectively unlimited. So if we're wanting to solve the web search problem where we learn from data to provide better responses to web queries, we have an enormous amount of data available to do that, and data is not the bottleneck. In natural language processing, for instance, a spelling correction problem, again, there are databases available where it's not the amount of data that's constraining how we're performing. In computer vision, again, there are prediction problems there where once again we have a huge amount of data available. So another way of viewing this is the amount of data available is effectively unlimited. No news here, but the way I want to look at that is that actually the performance that we have is limited by our computational resources. We shouldn't be thinking of it in terms of this classical viewpoint of the sample size. It's how much computation we can afford to throw at things. And just to give one extreme example, so Peter Norvig has this talk on internet scale data analysis, where he looks at an NLP problem and points out that, so his axe to grind is that we should be using all the data and doing very simple things with it. But the example there is, trivial prediction rules in this NLP setting with a huge data set, and he's able to use a huge data set because he's doing something so simple. Gave much better performance than more complex prediction rules, which restricted the amount of data that he could use to a much more modest size. But you can ask that, that really raises a question that you can ask in a quantitative way. If you have a limited computational budget, what's the best trade-off, right? Should you be spending your computation on going out and gathering more data and doing something very simple with it, or should you be spending your computation on estimating much richer prediction rules but with necessarily less data? And that's the large-scale model selection problem. Large scale in the sense that data is no longer a constraint. We want to work with computation. So where is it that we're focused on sample size in these model selection schemes and ora-cle inequalities that I described earlier? Well, so if we think about this complexity penalized model selection approach, the very simple one that I described first off, right? So we've got a hierarchy of classes, these models, F1, F2, and so on. We pick an empirical minimizer from each class, and then we minimize the sum of the empirical risk plus a complexity penalty, and that's the decision that we make. That's our f hat. So here we're solving an optimization problem for every one of these classes, and this argmin, that's a computation that grows linearly with, again I've used k, linearly with the number of classes that we're considering here, right? And then when we look at the results that we have for evaluating the performance of a model selection scheme like this, the ora-cle inequality that we had gave us the best trade-off between the approximation and estimation errors that we see, right? The best trade-off, the key point here is that that best trade-off really depends on the sample size. I mean, there's this small term here, let's ignore that, but the complexity penalty, this is the surrogate for the estimation error term, right? We're saying that the risk of the result of our scheme is close to the best we could have done across all of the classes. For class I, we have the best risk in that class, that's the approximation error term, plus something like the estimation error. But the estimation error, and therefore the trade-off between these two terms, depends on the sample size. If we have a certain sample, then there's an appropriate choice I here that's going to minimize this sum. As the sample size goes up, we would expect the complexity to increase, right? And we're getting the optimal trade-off with respect to a given sample size. And so what I'd like to do instead is consider ora-cle inequalities that give us the best trade-off for a given amount of computation, right, rather than for a given sample size. Okay, so I want to just introduce some notation for talking about that computation. So for being a little quantitative about spending a certain amount of computation. So we had this notation, gamma I of n, as the complexity penalty for class I, or fi, with a sample size n. I want to talk about the complexity penalty for a class with a certain computational budget. What does that mean? Well, I don't know. I'm being specific about, I'm brushing the details, the specific algorithmic details of how we solve the optimization problem, for instance, the empirical risk minimization problem for class I. I'm sweeping those details under the rug and saying, look, if we have a computational budget T, then that means we can afford in that time, under some model of computation, to go out and gather a sample of size ni of t and solve our estimation problem for class I. And then we'll call pi of t the complexity penalty that we get for the amount of data we can afford to go and get when we've got a certain computational budget. Okay? So that's the corresponding complexity penalty when we've got this computational budget. I'm just making an assumption that we're using a particular algorithmic approach and making no claim that that's optimal. Okay, so pi of t is our complexity penalty when we have a budget of t, and then we can rewrite the sorts of assumptions we want to make. So for instance, the simplest case where we look at deviations between risk and empirical risk, we can write that in terms of this complexity penalty, right? But now we're thinking of the deviations that arise when we have a certain computational budget. Well, we can write that as something like the complexity penalty pi as a function of our computational budget. Okay, and so when we have this sort of inequality, then we can conclude that, well, if we do empirical risk minimization over the sample of whatever size we can afford to gather for the ith class, the risk that we get is close to the best in that class, plus a penalty that's of order pi of t, plus an additional excess risk that's of order pi of t. Okay, and so what we want is an analog of these ora-cle inequalities that's expressed in terms of computation. So we'd like to come up with a model selection scheme that produces some decision f hat that does almost as well as the best we could get from any of our models, right? Minimizing the risk over all models, or minimizing this bound on the risk, but the bound on the risk is in terms of the computational budget. So it's like saying an ora-cle told you to use class I, right? And then we went and spent our full computational budget on class I. That's the bound on risk that we could hope to get in that case. And we're wanting to do that, spending the same computational budget, and do almost as well as the best across all of the classes. So it's the analog of these ora-cle inequalities, but in the case where we're measuring the difficulty of the problem in terms of the amount of computation that we have to spend rather than the sample size. Okay, and it turns out, we can't quite do this well. We actually incur a cost that's something like logarithmic in the amount of computation that we spend, right? So it's like we're not quite getting our full computational budget. It's a factor log t worse. All right, so let me say a little bit about the simplest approach to solving this problem. We could imagine allocating if we've got k classes, we could just allocate our budget uniformly across all of those classes, pick the appropriate sample size, go through and do the same thing, and we get an ora-cle inequality, but we get a penalty that scales linearly with the number of classes, and that's objectionable. But in the case and it turns out that you can't do any better if there's nothing more to be said about. So in general, if you don't have relationships between the models in your hierarchy, but if they are a hierarchy, if their models are ordered by inclusion, and these examples I described earlier are like that, then you can do better. So in the case when these things are ordered by inclusion, you can actually come up with a much stronger result. So same setting as the simplest case before, we have bounds on maximal deviations between risk and empirical risk in terms of some sort of a quantity gamma I of n, just as before. The point is, when our models are ordered by inclusion, then the empirical risk and the penalties are monotonic. As we increase the class index there, we're looking at bigger and bigger classes. They're ordered by inclusion. So our optimal risk and our empirical risk are non-increasing, and similarly our penalties are non-decreasing as we move up the hierarchy. And we can use that and exploit that, and the way we exploit it is by thinking in the space of penalties. If we can get within a constant factor of these penalties, that's good enough. So we can come up with a cover of these classes that just deals with, that, if you like, approximates the penalties for any class in here within a constant factor. And that's always going to be good enough for us. So it's a very simple approach. We just come up with a cover for the models. And we don't need strong assumptions to show that that's going to work. Well, maybe this is a strong assumption. If our loss is known to be bounded, right? And the computation grows at least linearly with the sample size, which is, we've got to look at the sample. And our penalty decreases no faster than, well, I've said 1 over n, but we can say essentially the same thing with any polynomial in there. Then we get just a logarithmic number of classes in terms of the amount of computation. Right? So we can cover all of the classes, all of our models with some called it a coarse grid that's only logarithmic in the amount of computation. And what do I mean by a coarse grid? What do I mean by covering? Well, we're getting these complexity penalties within a constant factor, right? So skip over that. So when we work with, there's not much on this beyond the notation, right? When we work with this subset of our models, and it's a small subset under these assumptions, then just doing the complexity penalized thing leads us to an ora-cle inequality that's exactly the right form. Right? We get a kind of a logarithmic penalty in terms of the amount of computation. So that's great. The one other thing I wanted to say is, in the more difficult setting with fast rates, we can do something similar. So in the case where the rates are faster than the deviations between expectations and sample averages, then it looks like we're in trouble, right? If we try the same approach, we try to allocate our budget to each class and do this empirical minimization plus a penalty. How is that going to work? Well, think about the empirical minimization here, right? The sample size, and hence the sample, is going to be different across different classes. So we don't have these nice relationships, right? When we optimize on a small class, we're able to go out and gather an enormous amount of data. When we optimize on a big class, we have to have a much smaller sample. and the correlations that we rely on to get our performance bounds are just not there anymore, right? So if we want to make optimal use of our computational budget, we need to have more data for smaller classes and hence different data. And so, you know, we can't make things work in the, we can't extend the previous approach in a simple way. But if we do a little more work, we can extend it. And all we really need to do is think of comparing the performance on a class. So when we're looking at a class I, we want to make sure that our penalized empirical risk for that class is better than anything smaller than it. All right? So these are smaller classes. We could have gone out and got more data, but in considering class I, we want to make sure that it does better than everything smaller than it. So these are kind of the computationally cheaper classes. And then, because we're working with the same sample size, we can work with the same data. We can use these inequalities that rely on the correlations, and working with the same data means we can get the analogous ora-cle inequalities. The fact that we're looking now at pairs of models means rather than a log t penalty, right, rather than a cost of, you know, we're reducing the effective computation in our ora-cle inequality by a factor of log t. It's now log squared t, but it's still polylogarithmic in t. And we get this sort of an ora-cle inequality that modulo this log squared factor, we're doing as well as if an ora-cle had told us which class we should use, and we'd gone and spent essentially our whole budget on that optimal class. So we're getting the best trade-off for a given amount of computation rather than for a given sample size. Okay, so there are several open problems here. You know, we don't have analogous results for the data-dependent case. You know, we don't know how to do it with structures that are more interesting than models that are ordered by inclusion. I think more broadly, it's interesting to ask this question of how can we get optimal performance under these computational constraints, rather than thinking in the more classical way about sample size as the measure of problem size. Okay, so the bottom line, you know, at least for the non-tutorial part of the talk, is for large-scale problems. I think this viewpoint of data being cheap and computation as being precious is really interesting and gives a different perspective. For the specific case of model selection, you know, we can look at the standard way of evaluating a model selection scheme, these ora-cle inequalities, and say, well, you know, we can formulate our problem in that way and say, well, we want to get performance that's near optimal in terms of the amount of computation that we're willing to spend. So it's as if we spent our computation on the near optimal model and didn't waste it on any of these other models. The thing is, we can do that with a cost that's something like logarithmic in the computational budget, as long as our system of models is nested, ordered by inclusion, and, you know, in the cases where we get faster rates, we can do it there as well for a slightly worse penalty. All right, so that's all I wanted to say.
Thank you.
Yeah, so the question is about this assumption, right? So when we say that we want to be able to come up with a coarse grid, so a small subset of the model hierarchy, where are we? Here. A small subset of the model hierarchy that suffices. Then under these assumptions, you know, it's straightforward to show that you only need a logarithmic number of a logarithmic size subset. So these are sufficient conditions, and you know, it's not essential to work with this sort of inequality, with this sort of a bound on the loss. I mean, that's kind of objectionable, for instance, in a regression setting. Or I should say it can be objectionable in a regression setting. In many cases, you know, how do you deal with unbounded losses and get results of this form, well, you're going to be working with a hierarchy of bounds on the losses as well. You know, so you're really working with this sort of assumption. The second thing to say is when you work with bounds on, for instance, deviations, so risk bounds in general, bounds on deviations between empirical and true risk, you're relying on concentration results there that need some sort of information about tails. And you know, to get these exponential inequalities, the typical thing is to consider, simplest thing maybe is to consider a bound on the loss there. So you know, it's going to be imposed anyway for those concentration inequalities. You can make milder assumptions and still get fast concentration, but you know, what impact does that have on this sort of requirement that you want to be able to cover the penalties? You know, that's a good question. I don't really know. This just makes things nice and easy, right? Because you know that the range of the penalties you have to deal with is fixed, and that's all you have to cover, right? Because once the penalty term becomes bigger than the biggest value of the empirical risk term, you're done, right? In fact, we could work instead with a quantity that was somehow distribution dependent. That's something like, you know, what's the empirical risk for a particular single function, like always predicting 0? What empirical risk is that going to lead to? And if there's a bound on that, that's good enough, right? You really only need a single function from the whole hierarchy to come up with the range of values that the penalties need to lie in. Right? So it's true. I mean, that's a good question. This is actually a stronger assumption than a considerably stronger assumption than you need.
Other questions? Let me actually ask something. So computation is one resource and one constraint.
Right.
What about communication, which seems to be a critical issue in modern architectures, actually?
Right. No, that's a very good question, and here we're just assuming that there is some underlying model of computation and algorithmic approach to solving the optimization problem you want to solve for each of these models, and you go ahead and do that for what is effectively a very small number of models. So in terms of communication, you know, when you're dividing things up into the different kind of chunks of computation, we're really thinking of that estimation problem you solve for each model as an atomic problem, and you know, it goes away and gets solved a very small number of times. So the communication complexity really doesn't arise. It's also swept under the carpet in this model of computation. But that's a great question. You know, what's the best way to do things when you have constraints of that sort as well? We haven't considered it at all.
Let's thank the speaker again.
Thank you.